All right, we're moving on to section 3.3, logarithms and logarithmic functions. Down here to the left, we have a graph of f of x equal to log base 2 of x. And we're asked to use the transformation rules that we've learned before to sketch the graph of log base 2, quantity x plus 4, closed quantity minus 1. Now, before with transformations, we talked about, am I impacting the inside or the outside? The same concepts apply here. This plus 4 is inside. And when I manipulate on the inside, if we remember, it does the opposite of what it looks like it would do. So this is log base 2 of quantity x plus 4. So that looks like a move to the right by 4 units, but it's actually left 4 units. And then the minus 1 is on the outside, and that does exactly what it looks like. Move down 1 unit. So what do I have? How is this going to sketch out? Well, let's find some points that we see pretty obviously here. This is the original. This is log base 2 of x. So that is 1, 0. That is 2, 1. And let's find another place where I cross just about 4, 2. And what I do is I move each of these left 4 units and down 1. So 1, 2, 3, 4, and down 1. I'm doing a dance step. 1, 2, 3, 4, and down. 2, 1 goes 1, 2, 3, 4, and down. And then 1, 0, 1, 2, 3, 4, and down. And what am I looking at? It's the same graph, but it's just been shifted down. So that's the idea of sketching it. So manipulate the inside, just like when we were dealing, so think back to when we had a parent function x squared, and then we were asked to deal with x plus 1 all squared minus 3. That plus 1 on the inside made it go left 1 unit. The minus 3 on the outside made it go down 3 units. If you do this, if you're looking at this for transformation, you're not quite understanding, what you can do is just, you could also go over to g of x and just plug values in, right? Plug in 0, plug in 1, plug in 2, and see what you get, and then plot that new point. Now, logarithmic functions have forced us to consider a new domain issue. Previously, the domain issues, the only ones we cared about were if the variable is in the denominator, we have to remove all values of x that make that 0. The second one was if I have a variable under an even root, I could end up with a even root that gives me an even root with a negative number under it, which leads to an imaginary solution. So those are the two things. What we're adding is the argument of a logarithm must be greater than 0. Okay, what's inside the parentheses, that's the argument. So let me give you a log x minus 3 plus 7. This is the argument. This is the term that I use, right? It's what's going in. It's log of something. So that's the argument. So the argument must be greater than 0. So what do? We take the argument, set it greater than 0, and solve. And the result is the domain. So take a look at f of x is equal to log base 8 of 4 minus 6x. We still have to consider the first two rules. Is there a variable in the denominator? No, there's no denominator. Is there a variable under an even root? No, there's no even root. So check for step 1, check for step 2, but then step 3 says the argument, which is 4 minus 6x, must be greater than 0. Not greater than or equal to, greater than. And then solve this. Negative 6x, I wanted to write the 4. Oh man, I got excited. Subtract 4 from both sides, and then get x by itself. Divide by negative 6. Divide by negative 6. And I divided by negative, so my inequality changes directions. Negative 4 divided by negative 6 is 4 over 6, which reduces to 2/3. So the domain of f of x is everything less than 2/3. So that starts out at negative infinity and goes all the way up to 2/3. Okay, if you run into one of these and we also have variables in the denominator and also have a variable underneath the root, you have to take into account all 3 of these. The resulting domain would be whatever step 2 and step 3 have in common and what is not in step 1. So we have to consider all of the arguments. But for the logs and for this chapter, it's mainly just going to be if there's a domain question, it's mainly just going to be about the argument. All right. Now we can move between exponential and logarithmic functions. These exponential functions and logarithmic functions are inverse functions of one another. So that means I can rewrite log base b of a is equal to y. I can rewrite that as b to the y equals a. So how does that help me? Across the top you can see, what have I got here? B is 3. A is, which one is A? A is on the other side of the equal sign, so A is 9. And Y is 2. Okay? This concept just kind of results from the log, just the use of the log. Log base b of a means what number do I raise my base to get a? And that number is y. And this is what it says right here in algebra. B raised to what number equals a? That's why these get swapped out. So 3 squared equals 9 can be rewritten as log base 3 of 9 is equal to 2 because what power do I raise 3 to get 9? 2. So let's do the same step down here, but now variables have come to play. So same idea. So I know I can convert this to log. The base is what? Well, look up here. The base is the thing that has a power raised to it. And so that's b. So b is 4.3. So when I convert this to logarithmic, that's log base 4.3. And then what goes in the parentheses is a. Which one is a in this format? Well, the 80 is because it's on the other side of the equal sign by itself. And then that equals what? Remember, log base b, log base of 4.3, log base 4.3 of 80 means what power do I raise 4.32 to get 80? Which is the power. The power is y. So y goes to the other side of the equal sign. Okay? Practice on this is what it's going to take. Now we're going to go back and forth. Again, if it helps, you can name b, that's the base. You can name a, that's the argument of the log, so it's 19. And then you can name y, which is 1.2. And then just remember your exponential form, b raised to the y equals a. All right. Next, okay, and if that helps, we can kind of label that out each time. Log base 4 of 64 is equal to p. The base is 4. The argument is 64. The y is p. And what's the base? What's that exponential form? B raised to the y is equal to a. Could you do the math there? You could probably solve that for p. What power do I raise 4 to get 64? What does it do? 4 times 4 times 4. So if I continued that problem, 64 is 4 times 4 times 4. So it's 4 cubed. So we'd find that p is 3. But the point of this section, the point of this is just to get you used to this conversion between logs and the logarithmic form and exponential form. Next, 8 to the negative 2 is equal to a. The base is 8. The argument, I don't have an argument because I'm in exponential form, so I have a power. Power is negative 2. And then a is a, because that's the letter that came along to play. So let's go back and look. Log base b, b is 8, of a, which is a, is equal to y, which is negative 2. Now you're going to see the next two, the next one doesn't have any variable in it, so we can reduce this a little farther. Same thing for the bottom. When we manipulate this, we're going to end up with a logarithmic form that we can then reduce. So 10 to the third is equal to 1,000. All right, so my base is 10, my power is 3, my argument is 1,000. So that means log base 10 of 1,000 equals 3. Now, log base 10 is a special log, and that's called the common log. And it's so common that when we write it, we actually don't write a base of 10, we just write log of x. So this is log of 1,000 equals 3. All right, that's how that's written. All right, and then the next one, same concept, different number this time. E to the 3.4 is equal to m. The base is e. The power is 3.4. And then the argument, or a, is m. So when I change this from exponential to log, that's log base e of m equals 3.4. Log base e of x is the natural log. Okay, and it's always rewritten. Log base e of x is written as, yes, that's cursive. Yes, it needs to be in cursive. ln of x. So again, I've introduced the common log, which just means it's a log with base 10. The natural log is a log with a base of e. So log base e of m gets rewritten as the natural log of m is equal to 3.4. These are going to be the ones you use mostly because change of base formula can be confusing, and a lot of calculators don't allow you to don't allow you to plug in logs that don't have either base 10 or base e. So you're going to see natural log as we move through this chapter. It's going to become more and more popular. Now, how about finding the values of logs? All right, so on the left-hand side, we're going to go through this without a calculator, and we're going to find the value of the logs without using the computer or without using a calculator. We're just going to think about it. So what does this mean? Log base 4 of 16, and I'm going to add a little piece here, okay? Equals x, okay? The only I'm bothered by when logs are sitting there and there's no equal sign, because you can't convert this to exponential form unless you have something over there on the right. So I've got log base 4 of 16 is equal to x. What does log base 4 of 16 mean? It means, what power do I raise 4 to get 16? If we convert this, that's 4, convert this from logarithmic form to exponential form, that's 4 raised to what number equals 16? And you know how to do this. You could probably do it without the work. If I can get the same bases, the powers are equal, x equals 2. Okay, and we're going to stay on the left-hand side. Log base 2 of 1/8. Again, I'm going to write equals x. What power do I raise 2 to get 1/8? You might be able to do this without too much work. 2 to the x is equal to 1/8. I need to use that exponential rule that if I can get the same base, the powers are equal. Well, 1/8 is 8 to the -1 because 8's in the denominator. It's supposed to be in the numerator. I'll give myself just a little bit more room. 2 and 8. 8's a multiple of 2, so I can rewrite 8 as 2 cubed to the -1. When I raise a power to a power, I multiply. 3 cubed raised to the -1 is, or excuse me, 2 cubed raised to the -1. 2 to the -3, which means x equals -3. And if we go back and look at our problem, if I raise 2 to the -3 power, do I get 1/8? Yes, I do. Natural log of e, okay? Remember what this means. The natural log of e is the log base e. So this means the question, if I rewrite this in exponential form, I'm going to change colors here for just a second. This means e raised to the x is equal to e. There is no exponent on the right, so there is an understood 1 there. That means x equals 1, right? If the base and the argument match, the answer is always 1. If the base and the argument have the same base, then calculating the log is super easy. Next, we have log of 1,000. Remember what this means again. This is the common log, which means this is a base 10. So 10 raised to some power is equal to 1,000. 1,000 is 10 cubed. So x is 3. Right? And let's do the last two on this side. Log base 2.35 of 1 is equal to what? Or equal to x. I have 2.35 raised to the x equals 1. We've not seen this yet. Okay, we've talked about it in class before, but we haven't seen this yet, where I have an exponential equal to 1. And the property or the rule that we're going to use to make this work is anything to the 0 power equals 1. And I'm going to write that word down here. Now the only equals 1. The only caveat to that is 0 to the 0. So what this means is I have 2.35 raised to some number equals 1. The only number x can be is 0. And then lastly, on that side, log base 7 of the square root of 7. 7s are matching here, but I don't have a number raised to a power. Can I fix that? Yeah. Log base 7 raised, if I take the square root, that means I just really raised 7 to the 1/2 power. And now the question is 7 raised to some number x is equal to 7 to the 1/2, which means x is 1/2. Okay. All right, we finished up all the rewrites, calculating the logs without a calculator. So now we're going to go down the right-hand side of this page. And what I want you doing here is literally using the calculator. So you can do this with a standard calculator, or you can do this with Desmos. Either of those is fine. And what we're going to do is round. So log of 15, and I want you to think about the answer here. Let me just show you what I mean by use Desmos. So log of 15. All right, 1.176. What does that mean? I want you to think about what does that actually mean. This means that 10 raised to what power is 15? All right. And then I got log of 0.343. That actually rounds to negative 0.465. These are estimates, so that is not going to be perfect. If you plug 10 to the 1.176 into a calculator, it's not going to give you exactly 15, but it's going to be super close. This one's negative. Why is that? Because I'm raising 10 to a power and getting a number that is less than 10. So the power has to be negative. Next, natural log, same situation. I have the base is e, which is 2 and some change. So that means my power is negative. I am missing a log, and I was going to draw this one out or point to it because you'll notice I don't have parentheses around this. Okay. Now in Desmos I didn't put parentheses for the first one. I'm going to do the same thing here. You're going to see me use parentheses because it's the way I was trained. I was trained when calculators weren't, that you needed to force the calculator to do things in order operation mode. So you'll see me use parentheses more than most instructors. I was also instructed by a man who loved calculators, and he was always just talking about calculators. Didn't like computers, loved calculators. So anyway, so log of 1,920 is 3.283. And I'm 3.2. That's an 8. 3.283. I don't know why I didn't type that one into the notes, but I didn't. Natural log of 55. What power do I raise e2 to get 55? Turns out that's just a bit over 4. And then natural log of 8,200. What power do I raise e2 to get 8,200? And the answer is just a bit over 9. All right, so we understand, we've gone through enough examples, we get what a log is doing. Log of a number means take the base, raise it to what number to get the argument of the log. That's what logs are. So how about some basic properties? Okay, well, we've run into these whether directly or indirectly. Basic properties. If you have log base b of 1 is 0, because b to the 0 is always 1. You've seen this before when if I had 1 to the 2.35 to something gives me 1 and the answer has to be 0. So if you ever have log base b of anything, any number here equals 0, then then what I have here, if I'm taking a number and raising it to a power to get 1, turns out that the variable has to be 0. The log has to equal 0. Next, log base b of b is 1 because if remember if the base and the argument match, then the answer is 1 because what am I doing? B raised to what power gives me b? 1. If I have the log of where the base and the argument have the same base, but my argument has a power in there, log base b of b to the x, just equals x because, again, that's the essence of what log means. What power do I raise b to get b to the x? X. And then lastly, this one is, remember we talked about logs and exponentials are inverse relation or inverse functions. So b raised to the log b is equal to x because log base b of x is equal to log base b of x. All right, so those are our basic properties. So let's use these properties to evaluate some logs. Log base 3 of 1. 0. Anything, what do I raise 3 to get 1? 0. I'm going to run down. You're going to see similar patterns here as we go. Next, log base 16 of 1. When the argument is 1, the power is always 0. Next, log base 3 of 3. The base and the argument match. So what is this saying? Just as a reminder, this is 3 to some number equals 3. What is the number? It's 1. 16 raised to some number equals 16. What is the number? 1. 144 raised to some number equals 144. What is that number? 1. Next, now I'm going to have my arguments where the bases match, but I have a power. So log base 3 of 3 to the 7th equals what? Okay. And again, I know the rules are right up there above. I know we just talked about them. 3 raised to some number is equal to 3 to the 7th. What is that number? Well, same base, exponents are equal, x must equal 7. Okay. Log base 16 of 16 squared. This always just comes back down to the power. What power do I raise 16 to get 16 squared? 2. Log base 144 of 144 to the negative 1. What power do I raise 144 to get 144 to the negative 1? Negative 1. And then lastly, we have an exponential, and then the log is in the exponent. Log 5 raised to the log base 5 of 3 is 3. It's always the 5 and the log 5. Just deal with each other and leave the 3 for us to play with. Or leave the 3 behind, I should say. All right, so basic properties of logs. Now we're going to do some evaluation. We're going to evaluate some of these and see if we're getting more and more comfortable with them. So down below, you'll see this in this will be skill practice 6. I'm asked to evaluate these. Typically, that means no calculator. Usually, you'd be directed to use a calculator. So log base 13 of 13. We just saw that. If the base and the argument match, the answer is always 1. Natural log of e. Again, remember this means log base e of e, right? Natural log is log base e. E, what power do I raise e to get e? The answer is 1. A to the log base a of 3, right? Whenever I do that, what have I got? It's always the argument of the log in the power. Natural log, e to the natural log of 6. Remember, this is e to the log e of 6. Base and the exponential base and the base of the log match. So I'm just left with 6. And then log base pi is log base pi of 1. What power do I raise pi to get 1? Anytime that argument is 1, the answer is 0. Let's go down the other side. Log of 1, we just talked about that. So again, in essence, what's going on here? 10 raised to some power equals 1. What is that power? The only way to get 10 raised to some power equal to 1 is if you've raised it to the 0 power. Log base 9 of 9 raised to the square root of 2. When the bases match, what does this mean again? This means 9 raised to some power equals 9 to the square root of 2. What is that number? It's the square root of 2. And as you do more and more of these, you're going to start saying, oh, whenever the bases match and I have a power, it's just the power that goes out. Log 10 of e. What does this mean? This is the common log, right? So this is log base 10 of 10 to the e. Take 10, raise it to some power to get 10 to the e. What is that? E, right? It's just like the one above. It just doesn't quite feel like it because the common log is in there and the natural log is in there.